Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed about the different effects like stiffness effect, permeability of stone column, and then the drainage effect like permeability and the clogging of the stone column, then smear effect, and how these effects influence the drainage performance of the stone column. So, I have already discussed that in case of seed and Booker approach, it is assumed that the permeability of stone column is infinite, but in actually it is a finite value. Then the stiffness of the stone column, because stone column is a stiffer material compared to the surrounding soil, so that was also not considered. And then this clogging effect, smear effect, those were also not considered. So, and without considering any effect, that Seed and Booker proposed these design charts, and I have already discussed about these design charts. Now, few researchers have worked on this area, and they have proposed a model to incorporate the smear effect or the permeability of the stone column, and based on that, it is been observed that definitely if I consider the finite permeability of the column, then the RU value will definitely increase, and I have already discussed that thing, that will increase. But if I consider the stiffness, that will act as a positive effect. So, it will dissipate the water in a faster rate. So, that is why the RU value will decrease. And then if I consider the smear effect or the densification effect, then due to the reduction of the soil permeability, due to reduction of the permeability of the soil surrounding the stone column or close to the stone column, the drainage performance will be reduced. Okay, so that means the water pressure ratio will increase. But if I consider the clogging effect, then it has been observed that clogging effect is not that significant during the earthquake, but after the earthquake, when there will be only dissipation of water pressure, that time the clogging effect will show significant, influence, because there is a sufficient time has to be given to material to flow, or the final soil particle to flow with the water and block the pores of the columns. Okay, but in case of second earthquake, if during an earthquake, if the column is already been clogged, then for the next earthquake it will show significant effect, or it will reduce the drainage performance even during the earthquake. Okay, and as well as after the earthquake also. And so you can see that the clogging effect mainly in the initial stage or initial earthquake, so it will influence the dissipation time. So, because of the clogging of the pores, the dissipation of water pressure, that time will increase. Okay, and we have already discussed. So, in case of optimum clogging, that means there is a optimum clogging. After that, what will happen when the water again hit those clogged pores? Then those clogged particles are been destroyed, or then when they are being destroyed, then these clogged particle will again flow with the water. So, then this particle, these voids will be cleared, but again then when the other next particles will come, they will again block those pores. So, that is about the optimum clogging or the plug burst Now, what is the optimum clogging, when the plug burst will take place? So, there is very limited information is available. So, much work are needed, workers are needed on this topic to identify this optimum clogging or this plug burst phenomena properly. So, now I will discuss that that based on considering these effects, we have discussed about the 4 effects, that means the stiffness of the column, permeability of the column, smear effect and the clogging. So, out of these 4 effects, the clogging will not be incorporated in the model, the clogging will be prevented. We can incorporate this model in the model, and we can see that how the clogging effect influences the drainage performance of the column. But during the design, this clogging effect, it is better if we want to incorporate it. So, rather than, it is better to prevent that clogging. Okay, so I will discuss that part. You can incorporate the clogging effect also, but here the idea is that we will incorporate the other effect, because other effects we cannot neglect, because permeability of the stone column we has to consider, the stiffness of the stone column we have to consider, the permeability of the stone column we have to consider, and then the smear effect, that also we cannot prevent. Okay, because these smear effect is a short term effect that during the installation these will occur. So, we have to consider these effects, or someone has to consider these effects. Okay, so but this clogging effect we can prevent. Okay, so that we will discuss later on, but right now we are discussing about, or we will discuss about the design chart. Those are being developed considering the other effects. So, how we can consider the other effects? So, here these charts are developed similar to the Seed and Booker, that here the main thing is that here that Ks is the permeability of the soil, but Kc is also considered, that is the Kc which is permeability of the stone column. Okay, so that means permeability of the stone column is considered. It is not infinite permeability, it is a finite permeability. Another one you can see MBC. MBC is the coefficient of volume change of the stone column. So, initially it was only MBS. Okay, that was the your coefficient of volume change for soil. So, now the coefficient of volume change for the column is also considered. It is basically coefficient of volume change. This means the compressibility we are considering. So, that means, and compressibility means it is stiffness we are considering. If the material is more stiff, then stiffer material, it is less compressible, and so that means the stone column is more stiffer than the surrounding soil, but less compressible than the surrounding soil. So, that means this compressibility effect or the stiffness effect is being incorporated. Then Kc, the permeability of the stone column is being incorporated here in these design charts. Okay. So, now in addition to that, the H is the thickness of the liquefiable zone or the stone column. So, that means how we will identify, I have already discussed how we can identify the zone of liquefaction. So, that zone of liquefaction, within that zone of liquefaction we will provide the stone column, so that we can provide the faster rate of dissipation of pore water pressure. So, that H is the basically the length of the stone column or the zone of liquefaction. Okay, or better way it should be the length of the stone column. So, now this, in addition that there is C and B, because x axis is that term, okay, that Kc MBC A square divided by, sorry, Ks MBC A square divided by Kc MBS C square. But here, I mean, as I mentioned, the different researchers have used different terminology. So, that here C is nothing but the diameter of the radius of the column. So C is nothing but RD, radius of the drain or radius of the column, and here you can see C by B, B is nothing but RE, radius of the influence zone. So I can say C by B, which is the same as RD by RE in the previous design charts, that is RD by RE, which is the same as C by B. Clear? And U max, you can see this is the U max. U max is nothing but RU. So U max this is the RU. So that means that it is the maximum water pressure ratio. So this is U max is nothing but RU, as I mentioned, and TAD I have already discussed in my previous lecture. So here these things are being incorporated. Two effects are being incorporated: the stiffness effect and the well resistance or the permeability of the stone column. Okay, so you can see these two effects are being incorporated and these two design charts are being produced. The first one is N EQ by NL equal to 1, next one is 2, then N equivalent by NL equal to 3, then it is for 4. Clear? So, and now I will discuss about the this equivalent. You can see the equivalent this M, you will get number of equivalent stress cycle. So you will get this chart. You can see for 7 it is 7.5, it is 15, then for 8 it is around 22, and for 8.5 it is around 32. Okay, so these are the equivalent number of uniform stress cycle. That is a function of the magnitude of an earthquake, that you know, that we have already discussed. Okay, now let's solve one example problem. The problem it is given: consider a soil layer with thickness H equal to 7 meter. So that means this whole 7 meter, that is a liquefiable zone. So then, and the Ks, the permeability of the soil, S means the soil, C means the column. Permeability of soil is given, the MVC, coefficient of volume change, that is also given for soil, and this site is subjected to an earthquake that is characterized by 24 number of equivalent uniform stress cycle. Okay, so that is characterized by 24 number. So you can see that this is 24 will be around here. Okay, so it is 8.2 around earthquake. Okay, so and then uniform stress cycle in a period of 45 seconds. So that means the duration of earthquake is around 45 seconds. Okay, now from the laboratory test, it is determined that the under undrained condition 12 cycle of cyclic stress would be enough to cause the initial liquefaction. So that means, as I mentioned, the N equivalent is the stress that will generate or that will apply during the earthquake. This that number of cycle, that cycle will be applied during the earthquake, and NL is the cycle required to cause an earthquake. So my N EQ by NL, this ratio will be 2, because we have a chart for N equivalent by NL equal to 1, 2, 3, 4. That is for 2. So here 2th cycle, the soil will liquefy, or the initial liquefaction will occur at 12th cycle. Now the stone column having diameter, I have given the stone column range of diameter is around 0.5 to 1 meter. So, and I have taken here 0.6 meter, but sand you can take it 0.8 meter also during your design. But for the initial trial, I have taken here 0.6 meter. So stone column diameter is taken is 0.6 meter, which is within the range. Are used to mitigate the liquefaction. The coefficient of permeability of the stone column is 200 times greater than the permeability of the soil. So it is not infinite, 200 times greater than the permeability of the soil. And volumetric compressibility or coefficient of volume change, that volumetric compressibility of stone column is 3 times smaller than the or lower than the surrounding soil. So that the compressibility of the stone column is 3 times lower than the surrounding soil, and the permeability is 200 times more than the surrounding soil. Now we have to design it. So we will first design it without considering any effect. That means permeability, compressibility we will not consider. So without considering any effect, that means that is the Seed and Booker approach 1977. Okay, so here first you have to calculate the TAD. What is TAD? TAD is KAS by gamma W MBS into TD divided by MBS into 1 by RD square. Okay. Now here Ks value is 2 into 10 to the power minus 5 meter per second. Then gamma W, if I consider 10, because we are considering gamma W, it is given 10 kilonewton per meter cube. Then TAD is the duration of earthquake, which is 45 seconds. Then MBC is 4 into 10 to the power minus 5. Okay, and then the 2RD is equal to 0.6 meter. So RD will be 0.3 meter because diameter of the stone column is taking 0.6 meter. So radius will be 0.3 meter. So it will be 0.3 meter to the whole square. So this value is around 25. Okay. So TAD is 25, and what are the other things required? So if I go to these charts, because I will read these charts, because NQ by NQL is 2. Now under which design pore pressure ratio? What would be the design pore pressure ratio? That is another important thing. Because generally, if you see the chart, it is developed for 0.4, 0.3, 0.5, 0.6. So RU value, you know, RU value is 1 means that is the initial liquefaction or liquefaction is initiated. But definitely we will not design it for considering RU equal to 1, because then the liquefaction will occur. No? So that's why we will design it for a lower RU value with some factor of safety. That's why generally in the field this RU value or Umax value is taken as maximum 0.6. That is the design value. It has been also observed that if beyond this 0.6, because what will happen as your RU value increases, that means your strength reduces, and stone column for its stability it needs the strength of the surrounding soil. So if your strength reduces, that means it is not means 1 means liquefaction, but if it is close to 1, still the strength will reduce. No, there is a generation of excess pore water pressure. So we will not allow to generate that much of pore water pressure, so that the strength will reduce in that level that there will be the stability of the stone column will be disturbed. So it has been observed that if your pore water pressure ratio is greater than 0.6, then there will be a stability issue in the stone column. So generally that's why the maximum design RU value or pore pressure ratio is restricted 0.6. Okay, that is one recommendation. So that means we will not design our structure or this ground considering more than 0.6 RU value. So here that's why charts are given up to 0.6, but here the chart is given for 0 to 1, but you will maximum go up to 0.6, because rest of the things is your factor of safety, or you will not allow that pore pressure to generate in that level. So your strength will be very or there will be reduction in the strength, so there will be stability issue in the stone column. But here for this particular case, we will design it for further lower RU value. So we will design it for RU value or Umax or RU value of 0.4. Okay, so that is our choice. So I will, but you can go up to 6.6, but we will design it at 0.4. So now if I go to this chart, you can see this is the chart we will use where TAD is 25, that means this is 25 and your RU is 0.4, that we are taking RU is 0.4, this is 25. Now your RD by RE, that will be, this is around 0.27. This is around 0.27. So this value will be around 0.27 because this is 0.2, 0.3, 0.4, around 0.27. So we will get the RD by RE as around 0.27. So it will be your RD by RE is equal to 0.27. Okay. So I can see that my RE will be equal to RE will be equal to your RE is equal to RD divided by 0.27. What is the RD value? RD value is 0.3. So it is 0.3 divided by 0.27. So it is 1.11. Okay. So now S, we know that for triangular spacing or for the square spacing, we know the square grid. So we know if we are designing for square grid. Okay. So for square grid, our R2RE is equal to 1.13S. Okay, so from here now I have the RE, so S value will be equal to 2RE divided by 1.13. So this is 2 into 1.11 divided by 1.13, so that will be 2 meter. So for the spacing of the column for the square grid, if I don't consider any effect, then this should be what are my design parameters? My design parameters will be what would be the spacing, what would be the diameter of the stone column and length of the stone column. So length of the stone column will be decided based on your how much is your liquefiable zone. So based on that you will decide that how much is the liquefiable zone. So now the spacing and diameter you have to decide. So that means here the diameter we were taken during our design is 0.6 meter for column. Now spacing is been determined as 2 meter, which is the range, because range is 1.5 meter to 3 meter, that is the range of spacing that we have given. So it is within the range, it's okay. So that means the final if we consider this Seed and Booker approach, so based on their chart we are getting for a diameter of stone column 0.6 under square grid. Under this condition we have to provide a spacing of 2 meter. So now let's consider those effects. First the two effects of stiffness effect and the permeability effect. So for that purpose we have to calculate the Ks divided by Kc and MBC divided by MBS into H square by C square. So you know that is the thing. There is a Ks divided by Kc, MBC divided by MBS, H square by C square. Clear? So we have to calculate that. So now here C is equal to 0.3 meter because C is equal to 2 DC. 2C is equal to DC, which is equal to 0.6 meter. DC is the diameter of the column. Now if I put this value, here I can write that 1 by Kc by Ks, okay, and your this 1 by MBS by MBC, and then this is H by C whole square. Now what is Kc by Ks? Because Kc is 200 times faster than Ks. So this Kc by Ks ratio, that is equal to how much? 200, because Kc is 200 times faster than Ks, and your MBS is MBC. This ratio is how much? This ratio is 3, because MBC is 3 times smaller than the MBS, or MBS is 3 times more than the MBC. Because the compressibility of the soil is 3 times more than the compressibility of the column. So you can see that we can finally write this is 1 by 200 into 1 by 3 into H is 7 square and C is 0.3 meter. So it is equal to 0.91. This is equal to 0.91. So and TAD will not change, TAD is still 25. So now I will go to this chart. This is 3, this is 4. So I will go to this one. This is NQNL equal to 2. So here this value is 0.91. So this is 0.1, this is only 1. So this is 0.91 is here. And you can see our chart is this TAD value is, you can see 200 is this black dot, and this 100 is this white triangle, then this 50 is this black diamond shape, and 25 is white triangle. So you can see 25 is white triangle, and so that means, and 0.4 is this line. 0.4 is this line. So we will find that this is these black dots mean 200. This triangle, white triangle in upward direction is your 100. Then this diamond shape black is 50. So our is this one, this triangle in a flat triangle of white dot, and this one is your this is double dot, though this is for 0.3, this is for 0.4, this is for 0.5, and the farm line is 0.6. So this is our line, and this one is our actually line, this line. So we will go for this line and corresponding to this line. Okay, so this is the point, because this line is for 0.4, which is the RU value. This one is for 0.5, and then this is for this is for your 0.6. This is for 0.5, and this is for 0.3. This is for 0.3. So we have these points. So here, because this is your flat triangle, so this is the line. This is our line of interest. RU equal to 0.4 and this TAD is equal to 25. This is the line. Okay. So this is 0.91. Then this value is around C by B is around 0.32. Okay. It is 0.32. So if I consider that, now my C by B from the chart, that C by B is equal to 0.32. That is from the chart. So here you know that C is equal to basically RD and B is equal to basically RE. Okay, same meaning. So I can see that from here B will be equal to C by 0.32 and C is equal to 0.3. So this is divided by 0.32. So it is 0.94. Okay. So similarly I will get S will be your 2B by 1.13, same logic, because here also S equal to RE equal to B, 2 RE but 2B by 1 by 1.3, because same square root we are using. So this will be your 2 into 0.94 divided by 1.13. So this will be coming out to be 1.66 meter. So that means if you see that if we were not considering any effect, then it was 2 meter was the spacing. Now we are considering the permeability and stiffness, and we know that permeability has the negative effect. If you consider the limit permeability or finite permeability, then definitely your RU value will increase as compared to the case if you consider the infinite permeability. But the stiffness has positive effect. If you consider the stiffness, your RU value will reduce, but the permeability effect is more significant compared to the stiffness effect. So that's why the net RU value, if you consider both permeability and the stiffness, because permeability has higher effect or the effect compared to the stiffness. Though the permeability has negative effect, stiffness has positive effect. If you individually consider them, then stiffness will reduce your RU value and permeability will increase your RU value. But their combined effect, as the permeability has the higher effect or significant effect as compared to the stiffness, then overall the net RU value will increase. So what is the meaning of net RU value to the increase? So to make two things level, if your RU value increases, then make these things level, we have to reduce the spacing so that it will compensate that increase of RU value. Because if you reduce the spacing, definitely the dissipation time will reduce, and the amount of RU that was increasing due to this, considering this effect, then definitely your spacing you have to reduce, so that you can reduce the travel time and you can reduce that excess RU value. So, but that is other way you can see that if you consider this effect, then your required spacing will reduce. That means initially spacing was 2 meter, your travel time was slightly more. Now you have reduced the travel time. That means your water pressure will be dissipated in the faster rate, because we have considered that permeability and the stiffness, and overall net one is it was controlled by mainly the permeability. So that's why the required spacing is been reduced. Now if I consider the smear effect, okay, smear effect, if I consider the smear effects, so let me just draw this thing and the smear effect part. So now if I consider the smear effect, because now I told you that I have considered two effects, now we will consider the smear effect. Or densification effect. Okay, so then how it will be, how we can take care of that. So this is the stone column, this is your disturbed zone or the smear zone, and this is the influence zone, as usual influence zone. Okay, now obviously that this is C value, this is S small s value, and this one is the B value. So this is B, this is C, and this one is the small s or the smear zone. Now if I draw the your vertical section, so this is the total influence zone. If I take the half portion, this is our column, this is our smear or disturbed, and then the undisturbed zone. This is column. So in the undisturbed zone, due to the densification effect, your permeability will reduce. So that reduction is something like that. So this is the reduction will follow this trend. Then this is the undisturbed zone permeability. So that means this disturbed zone permeability, you can see it is been reduced due to this densification effect. So here this is Ks, permeability of the soil, and this one is the KSM. So Ks to KSM, KSM is the smear zone permeability. So it will follow a trend. Generally, it is followed by a parabolic variation. Similarly, the compressibility also. If I consider the compressibility, also, so this is my column. So if I compressibility will also reduce because of densification, so that will also follow a parabolic variation. In the undisturbed zone, this is undisturbed zone. So there is no variation because it is constant for the soil. But in the disturbed zone, it is the variation. It will reduce, and near to the column, the reduction is maximum. After that, because the influence the disturbance is maximum near to the column, then as we go away from the column, the disturbance will reduce. So here the maximum reduction near to the column, then this reduction will the permeability will slightly increase, and then it will reach to the undisturbed zone permeability or the compressibility. Okay, so this is also say MBS. So this one is MVSM. Okay, M means it is in a smear zone. Okay, so this is variation is this is a parabolic variation. Okay, so this is the parabolic variation. So now if I see that what would be the extent of that. So here in the next class, what I will do, I will discuss about this variation. Okay, because next class I will start a new module, that is your the seismic slope stability analysis. But before I start that module, I will show you this variation, how this what is the zone of this disturbance, how we can find how the U value will change, and how we can incorporate these effects in our design. Thank you.